Actually, not today. We are going to do word problems next class. Okay. Yeah, we are going to move on to the next bit of information now, and that'll lead us into word problems for next period. All right, hope everybody had a good weekend. Let's get this going. We're moving into chapter 12 now. Bless you. Okay, here we go. So, chapter 12 is called Graphing and Optimization. I have underlined the word optimization because this is really the most important concept of this chapter and what's going to be probably the most pertinent information for us. So, what is that word optimization? Does it have any meaning to you when I say optimization? Yeah, but what does that mean? What is optimal or optimized or?
The highest it can go.
Highest it can go, okay. Efficiency?
Oh, yeah.
Okay, so like, I don't know, the first thing that came to mind is like your car, right? You can get like, put real cheap gas into it and it'll run, but you won't get the best gas mileage, right? Optimizing something means making it the best it can be, I guess, we could say. I mean, there's different ways that we can look at this word, but for us in this class, what we're going to be looking at are cost functions, revenue functions, profit functions, and trying to figure out where we have these important things happening within the function, where we might have highest points and lowest points on our graphs. So the first section is called the first derivative in graphs. So we're going to look at how the first derivative, now we know how to take derivatives, right? We are going to look at how that first derivative, taking the derivative, somehow tells us about what a function looks like, what its graph looks like. Right? And then the second section has to do with the second derivative, which we have not talked a whole lot about. All right? So we are going to look at both of those things today. And then next class we will finish up 12.2. We're going to do word problems. So there's no word problems today, just setting up all the tools we need to do the word problems on Wednesday. All right, so I'm going to start with a picture. All right, so I'm going to draw something here for us, and I want us to just take a look at this and talk about some things. So now here comes a graph of a function for you. Let's say it goes up on the left like this. Say it comes down. Say it goes up here. Let's say it comes down. Does that little weird thing. Say it does that. And then goes like that. Now you don't have to draw perfectly if you're doing your own notes, just as long as you get the basic idea of what's happening here. Okay, does this graph have a maximum value? So when you think maximum, you should be thinking highest, a highest point. Does this graph have a highest point? Yes or no? Support your answer with some evidence. No, why?
It's open-ended on the...
Okay, so this little arrow actually means something, doesn't it?
Yeah.
That little arrow means this graph continues with this behavior up forever. So there is no highest point on this graph, is there? Okay. Does this graph have a lowest point?
No.
It doesn't, because this arrow implies that this continues down forever. All right. So there is no highest and no lowest point. But there are some interesting points that might require us to consider that, I don't know, like something like this point. That is not the lowest point on the graph, is it?
No.
Not on the entire graph, but locally, local is the word I'm using here, L-O-C-A-L. Locally, like if you just focus your attention right here, that is the lowest point on the graph, right? Right in this little area, this little region. It's kind of like, I don't know if do kids play that game King of the Hill anymore?
Yeah,
No?
I think they're allowed to.
Are they not allowed to? There's probably like an iPad app that they can play King of the Hill. Y'all know what King of the Hill was?
Push them off right there.
It's like a person tries to get on top of the sand, the dirt pile. You know, like you get up on the top and you try and stay up there and people try and push you off, right? And if you can stay on top, you're the king of the hill. All right, well, so there's a bunch of hills on this graph. There's different hills, and you can be, you know, the king of your hill, right? So maybe you're up here, you're the king of that hill, but maybe over here there's a different king for this hill. So when we say locally, we're saying just take a look around here. Is this the lowest point on the graph? Here. Yes? Is this the highest point on the graph? Here. Yes? Like locally, is this the highest point on the graph?
Yes.
Yes, locally, like right in here. If you just like ignore everything else, that's the highest point on the graph. How about this point right here? Is that the lowest point on the graph right in this little region?
Yes.
Yes. Highest point? Yes. So these points are actually important to us. They are called local minimums and local maximums, and I'm going to label them as such. This right here would be called a local minimum. This would also be a local minimum. This would be a local maximum. And this would be a local maximum. Okay? Now, there's something that this local minimum, this local maximum, and this local maximum all have in common in terms of the slope of the tangent line. So what is the slope of the tangent line at this point? 0. Because if I draw a tangent line, it would go through here, it would be 0. Do you agree? Yes? And up here, through there, it would be 0 also. Slope of tangent line here would be 0. Agreed? Okay, so I'm going to label that now. I want you to understand that right here, the derivative is 0. Doesn't the derivative represent the slope of the tangent line? Yes?
Yes.
That's what the derivative was? You all right?
Yeah, good.
Okay. Right here, the slope of the tangent line is 0. Right here, the slope of the tangent line is 0. Follow me? All right. Now, right here, this is a local minimum. Is the slope of the tangent line there 0? No. What we have here is something called a cusp or a corner. It's where a graph comes together at a point. Do y'all see it comes together at a point? Whenever you have this happen, let's just take our tangent line, let's just move it around here. Do y'all agree that this is what the slope would look like if I'm moving along the graph?
Yeah.
And then when I get down here, it's 0. I start moving up here like this, and then I get right here. Now what happens here is it starts to come down, right? And then it almost goes vertical, okay? It may or may not, it depends on the graph itself, but do you agree it's pitched down like this? Then something happens at the point. I'm not sure what, but then immediately the graph flips and starts going like this. Do you all see that, the tangent line? So it changes from a negative slope to a positive slope immediately, like in one step. Does that kind of make sense? Your derivative goes from negative slope to positive slope. See here, what happens at this point? What is my slope, positive or negative here? Negative, 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 still negative? Still negative? Still negative? 0, positive, positive, positive. See how that's a nice smooth transition from negative to 0 and then to positive? And then this one goes positive, what, to 0 and then negative. But then this one goes negative and then real quick switches to positive. And then positive, positive, positive to 0 and then back to negative. That kind of, that going in? Yes? Okay, so this point right here where we have that quick switching, the derivative is not 0 here. The derivative here is undefined. And the way you know that is because you have a corner there. Corner or a cusp. We also call those cusps. All right, so anywhere where we have a corner or a cusp, your derivative is undefined. All right, I have one more question before I point out one more important point on this graph. When we talk about slopes of tangent lines, we all agree that the slope of this line, flat line, is 0? That this is positive? That's negative, right? What is the slope of a vertical line? Straight up and down. So, I heard 1. 1 is this. A perfect diagonal, over 1, up 1, over 1, up 1. That's 1. 2 is over 1, up 2. 3 is over 1, up 3. 4 is over 1, up 4. 5, 6, 7, 8, 9, 10. What happens when I go vertical? Yes, it's straight, but what's the slope? It is infinity. It's actually undefined. Okay, it's undefined. You don't have a slope of a vertical line. Okay, so horizontal line, the slope is 0. Vertical lines, the slope is undefined. Okay? And remember, the slope is the derivative, right? So there's one more point on here that I kind of drew that has a crazy slope happening. Y'all see it? It's about right in here. So look at my slope. What's my slope here?
0.
0. Negative. Negative, right? And then what's happening to this line as I try and go right here? Doesn't it look like it's trying to go vertical? Right? So you have right in here somewhere, your derivative wants to go vertical, so the derivative is undefined. Okay. I'm going to ask you a question now. I want you to pay careful attention to what I'm asking. All right? If a function has a maximum somewhere or a minimum somewhere, then does the derivative have to be 0? No. Say it again. If a function has a maximum or a minimum, does the derivative have to be 0 there? No. Because, well, what? That's a minimum, right? And the derivative is not 0. But it's undefined, right? Okay. Let me ask you this. If, according to this picture, if your derivative is 0, must you be at a maximum or a minimum? If your derivative is 0, must it be a maximum or a minimum? On this picture, it looks like it, right? For this picture, it does look like that, right? If your derivative is 0, it looks like that's where a maximum and a minimum is going to occur. What's that? It's not always. From this picture, it looks like it might be always, right? Yeah, but see, we have this right here, right? So how can we kind of summarize what's going on here? Would you agree that the points where we have maximums and minimums are either going to be where we have a derivative of 0 or undefined?
Yes.
It looks like there's a connection between if the derivative is 0, if the derivative is undefined, we might have a maximum or minimum there. Yeah? Maybe? Now, this is undefined, right? And that's not a maximum. Right? So we have this thing where, look, the derivative being 0 or undefined can be important to us. In fact, wherever the derivative is 0 or wherever the derivative is undefined on a function is critical in us determining whether or not we have a maximum or minimum. The places where the derivative is 0 or undefined, those places are critical to us. And they have a special name. They're called critical points. That's what we call them, critical points. So I'm about to define that for you right now. We're going to say from here on out that the critical points of a function are anywhere that the derivative is 0 or undefined. All right? Got that? I'm going to write that down right here. Given a function f the critical numbers or you might hear it referred to as critical points are all values of x where 1, f prime equals 0, or 2, f prime is undefined. Okay, so from this point forward, if I give you a function and I say, hey, go find the critical points, what you're going to have to go do is figure out where the derivative is 0 and where the derivative is undefined. That's what you're going to need to do. All right? So let's just do one quick example, just so we can practice getting the critical points of a function. Maybe we'll do a couple of examples. Find the critical, let's see if the book's using points or numbers, I forget. Critical numbers, they call them critical numbers. Of f of x equals 3x squared minus 4x plus 1. All right, that is a parabola, right? If we were asked to graph this, this would be a parabola. It would open up like that. And I'll just draw a quick graph of it. We know that that parabola opens up, right? We are trying to find the critical numbers of this function. So how do we do it? Well, we need to figure out where the derivative is 0 and where the derivative is undefined. So let's start with the first thing. Let's just take the derivative. What is the derivative of this function? And we're taking the, I should point out, we're done with related rates, so we're not differentiating with respect to time right now. We're going back to like when we first did derivatives. Everything's with respect to x, all right? So what is the derivative of this? 6x, right, 6x, and then minus derivative of that's just 4, derivative of that's 0, so just 6x minus 4, right? Okay, that's our derivative. So I'm going to box it. This is important to us. Now, let's check the first thing. Where is the derivative 0? So I'm going to take that derivative and set it equal to 0. And solve that little equation right there. So I'll move my 4 over, right? And divide by 6. And reduce the fraction, I get 2/3. Is that okay with you? Yeah? So this is telling me that when I look at my graph, if I go to an x-coordinate of 2/3, so if I move on my x-axis to 2/3 and go and look at the function, I'm going to have a slope of a tangent line of 0 there. And what do you think that that corresponds to on this parabola? This lowest point, right? It looks like this lowest point right here is where that would be happening. This should be 2/3. That should be where it happens, where we get a slope of a tangent line of 0. See, derivative is 0. Now, we also have to check this. Is there any place where the derivative is undefined? So the second thing, where's the derivative undefined? Now, this is where things get a little bit weird, all right? It's almost weird because it's too easy, like it's too obvious that it's weird. Looking at this function, is there any value of x that I can't plug in here? Like, is there anything that's going to cause division by 0? Well, there's not a fraction, right? So you're not ever going to have division by 0. There's not a square root, so you're never going to have like a negative number underneath the root. You following me? Like, you could just plug any number you want in here, and you're never going to have a problem. 6 times that number minus 4. You're always going to be able to compute that, no matter what number I ever give you, right? So there are no issues with this particular function. This never happens. Now, I'll do another example where we will have this happen, but this one right here, there's no issues. Okay? So this, we don't have this happen. So there is only one critical number for this function, and this is it. Okay? And what we can say is that at that point, the derivative is 0, flat, right? Now, does this tell us that we have a local maximum or a local minimum here? Does this tell us that? No. Now, we know what the graph looks like, don't we? So it makes sense that this should correspond to a local minimum, shouldn't it? But that's only because what we know about parabolas. If we had no idea what this graph looked like, we would have no idea whether or not this was a local max, a local min, or neither one. Like, it could be nothing. It could just be some other place in the graph that we have a flat tangent line. Let me show you a quick graph. Look at this one right here. Look at this graph right here. Look at my tangent line. Positive or negative here? Positive. Positive still? What is it doing right around here? 0, right? And then it continues positive. Somewhere in here, it looks like my derivative is 0, right? But that's not a maximum or a minimum. So it is possible to have a derivative be 0 but still not be at a maximum or minimum. Don't worry, we're going to bring all this together in a minute. I just want to make sure you understand. When we're asking for critical numbers, this is the actual mechanics that we do. All right, so let's do another example. Let's do something like something that looks completely, I don't know. I don't know how it's going to look to you. Let's do this. Square root of x. So find the critical numbers of the function root x. All right, so what's the first step? Take its derivative, right? Okay, so if I'm going to take the derivative of the square root of x, I should probably remember that that's x to the 1/2 power, right? And then take its derivative. So the derivative will be what? 1/2 x to the negative 1/2, right? And that is the same as 1 over 2x to the positive 1/2. Because remember, a negative exponent means you can drop it down. And then this really just means square root of x, doesn't it? So this is just 1 over 2 root x. Any questions on that part? Sure? We're good? The two's already down here, right? So this negative exponent drops down, it joins the 2, becomes a positive exponent, and then x to the 1/2 is the root x. It's kind of like us going backwards from here to here. All right, now, first thing, where's the derivative 0? So we're going to take this derivative and set it equal to 0. How in the world do we solve that equation? How do you solve that for x?
Wouldn't we use that first formula up there on top?
What do you mean?
Like to get the...
On the last problem, didn't we have this? And we set that we set the derivative equal to 0? And then you just did some algebra, you moved the 4 divided by 6, and you got what x was, right? You were able to solve for x, was 2/3. How do we solve for x here?
change the bottom one, and you would have to end up with a 0, and you can't do that because then you end up with a 0 on the bottom. So you're going to get an undefined thing. That's the only thing you could do.
Okay, yeah, so let me try and explain this to you as easy as possible. I want you to just consider this for a second. Let's say that I have a fraction over here, a over b. Is that right? A over b. Here's a fraction. Let's say I set this equal to 0. Can't I always multiply both sides by b? Can't I always do that?
Yes.
Yes? And this b would cancel? Yes. And over here, 0 times anything should be 0. Yes. So this would be a is 0. A is still left here, and 0 is here. Agreed?
Agreed.
Okay, now why am I showing this to you? I'm showing this to you because this. If you ever have a fraction, if you ever see a fraction equal 0, all you have to really ask yourself is when is the numerator equal to 0? That will always be your solution. So when you look over here, you see a fraction, right? A over b equals 0. The only time this will ever be true is if the numerator is 0. So what's the numerator? 1. For this to be true, I would need 1 to equal 0, right? But that's not going to happen ever, right? 1's not 0, not today at least, right? 1 is not 0. So what does that mean?
Undefined.
Not that it's undefined. This equation has no solutions, all right? There are no solutions to this equation. Please remember this. A fraction can only be 0 if the numerator is 0. A fraction can only be 0 if the numerator is 0. So anytime you ever have to set a fraction equal to 0, just set the numerator equal to 0. That's all you have to consider. You can just throw the denominator away. So no solution. Are we done? Right now we're saying there's no critical numbers, right? Because we've set the derivative equal to 0, we got no answers. Anything else to consider? Where the second condition, right, for critical numbers, the second thing we have to check is the derivative undefined? This is a question. Is there anywhere where the derivative is undefined? So let's take a look at that derivative again. And I'll write it down here. 1 over 2 root x. This was our derivative, right? Are there any values of x that I cannot plug in here? A lot? What can't you plug in here? Give me an example of one number you cannot plug into this. 0, right? Because what happens? You'll get 0 on the bottom and you'll get division by 0, right? So you can't use 0, right? You all right today? Yes? 0 doesn't work? 0 doesn't work? Now, before I can call it a critical number, this is important, before I can call 0 a critical number, I have to go back up to the original function. Would 0 have worked in here? Yes. What, if I plug in 0 here, what's the square root of 0? 0. Yeah, the square root of 0 is 0. Because what number, when you say square root of 4 is equal to 2, you're saying what number times itself is 4, right? You say 2, right? So if I say square root of 0, you're saying what number times itself is 0? 0, right? So let's go back. I said, hey, what can you not plug into this? And someone said 0. And I said, yes. Can you plug 0 into this? Yes. So you have x equals 0 cannot go in here, but it can go in here, right? It is a critical number then. All right, so x equals 0 is a critical number. Somebody give me another number that I can't plug in here. 1. I can do square root of 1.
Oh, negative.
Negative. Negative what? Give me a number.
Negative 2.
Negative 2, right? Any negative number that you could think of, right? Let's go with negative 2. So negative 2 would make that undefined, right? However, can you plug negative 2 into this? No, you couldn't have. So to be a critical number, you have to work, you have to be able to plug it into this and not this. So 0, I could plug in here, but not here, right? Negative 2, someone said negative 2. That will not be a critical number because it can't go into this. We can't put it in here. So -2, chunk it. -3, same story. -4, any negative number you cannot plug in here. All right? So the only critical number we have is 0. Follow that? No? Just say it. Okay, so what can I restate?
Just the bottom part is kind of building up.
What, this or this?
Yeah, that.
What about this? You know where it came from?
Yes.
Okay. So I'm asking,
I'm just confused, like what numbers can go in there and not work.
okay, so are you comfortable with the idea we cannot take square roots of negative numbers? You're okay with that? Okay, so I cannot plug a negative number in here, right? Now, if I go in here, I can't plug a negative number in here either, right? So the way this works is you try and find numbers that don't work here, right? Like 0 doesn't work here, negative numbers don't work here. Any number that you pick down here that doesn't work, you have to see if it works in here or not, right? So we found 0. 0 does not work here, right? And it does work here. So it's a critical number. -2 doesn't work here, right? And it doesn't work here. Since it doesn't work in here, we can't consider it. You cannot consider a number that doesn't even go into your original function. You can't ask about what it's doing in the derivative if it doesn't go into the original function. So technically speaking, all critical numbers must come from the implied domain of the original function. But I don't want to get all too technical because I just know I'll lose even more people with it, okay? But this function has an implied domain. Critical numbers must come from the implied domain of that function.
There can be positive numbers that can be critical numbers too, right?
Yeah, we could have, not for this function though. Because see, if we plug a positive number in here, we don't have a problem, right? You need to have this thing be undefined, and the only way to make this undefined is either plug 0 in here to get division by 0, or a negative to create a negative root. If you plug 4 in here, for example, if I plug 4 in here, that's just going to give me a number, isn't it? That's not undefined. That's just a number, right? So I'm not even considering that as a critical number at all. It has to create a problem while simultaneously not create a problem here. Does that help?
Yeah.
Okay. Now the good news is that we're not going to deal with this issue much. We're going to be dealing more with this issue. But to be somewhat thorough, I have to at least entertain it. Okay? I'm sorry?
Or maybe finding 0 not defined.
We're going to look at both, but the problems that are going to come up in your homework and on the test are going to have this happen more often than this happens. Okay? That was just an example to show you how this whole undefined thing works. And it can be a little confusing, I understand that. All right. Let's do one more. And I think I'll pull one from the book so that I keep it from getting too nasty. Negative x cubed minus 4x plus 8. All right, find the critical numbers of this. So what's our first step? Take the derivative, which is
-3
negative 3x squared minus 4. Okay? And then, first thing with that, after we do that, set it equal to 0. So I want to know when is the derivative 0. So I take negative 3x squared minus 4, set it equal to 0. And now you have several options on how to do this, but I think the one that would make most sense to most people would be to move the 4 over, right? Make it a positive 4, and then divide by -3. So if I do that, I move the 4 over, it becomes positive 4. I divide by the -3, I get that. Okay, now what? We're solving for x. Take the square root. So we take the square root, and anytime we take the square root on both sides of an equation, we must do plus or minus. Does that sound familiar to you? Have you heard that before? Anytime you initiate a square root on both sides of an equation, you must consider both the positive and the negative. So I'm taking the square root of the left side, I get x. Square root of this side, 4 over negative 3. Here's the problem. This is a negative number, isn't it? And you can't take the square root of a negative number. Well, you can't. You're not allowed to use imaginary numbers. Okay, we're not. This class doesn't talk about imaginary numbers. We don't deal with them. So we would say here, there's no solution. There's no solution here. No real solution. No real number. All right. No solution here. Y'all clear on why that's no solution? Can't take the root of a negative number. This is a negative number. Okay, so there's no value of x that's going to make the derivative 0. The next thing we consider, the second thing, is anywhere that the derivative is undefined. So let's just take a look at that derivative. It was negative 3x squared minus 4. Is there any number that you can think of that you cannot plug into this? So what are the things what are the problems that we run into in a class like this? What are the types of issues that we could ever run into? Division by 0 and roots of negative numbers. That's it. For a class like this, that's all we ever have to worry about. All right? So do you see that we could either ever have division here? There's no division, right? So there's no problems with plugging in numbers and getting division by 0. We're okay with that. Do you see a square root anywhere? No, right? So I could plug any number I want into this and no problems. So is it ever undefined? No, it's never undefined, which means there's no solution to this either. There's nothing here, right? Do y'all get that? There's no value of x that you cannot plug in. Everything you plug in is good. And what we're looking for is things that cause it to be bad. So what can you tell me about critical numbers for this function? There are none. There are none. This function never has a derivative that's 0. It never happens. And it never has a derivative that's undefined. So it never has a corner cusp, or it never has, like that one I drew that did this. It never has a tangent that gets vertical like that. That function does not do that. All right? Let's do one little. Well, now I want to do one that's a little more complicated than that.
So that one would have a point of rotation, or like a point like that one. That point doesn't mean anything. That point has no significance for us in this class. Like
What point?
If it's a cube, then it would go like that, right? And the reason it never goes, there's no derivative, is because it never actually flatlines it.
Yeah, that particular function actually it was negative x cubed, right?
Yeah.
It actually goes something like
Yeah,
this.
So,
Yeah.
flat line. But is that center point where it pivots? Is that worth anything, or do we have to care about?
There is actually a point here that's important. It has to do with the second derivative.
Okay, but for this.
But for the first derivative, there's not a critical number.
Yeah, because algebraically, it was like,
Yeah.
there's no critical number, and I was just like, but there's like a point around
Yeah.
it. But okay, no significance. Okay, no significance.
So here, to help you out, when you look at the derivative of this curve, it's negative, right? And it's negative, 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 negative. It's always negative.
Yeah, yeah.
But it's never 0, and it never like flattens out, and it never goes to a corner or a cusp, right? So that's what's happening. Now the second derivative is going to tell us, there is an important point on there from the second derivative, and it actually it's somewhere around here. But we'll talk about that, and we'll talk about that later. Okay. All right, so how about this one? How about this? X squared, or x cubed plus 2x squared plus 3x. Okay, first thing we do, Find the derivative. Okay, so we find the derivative and we get 3x squared
Plus 4x plus 3.
plus 3. Hold on a second. I'm going to change one thing on this problem because I want it to work out a certain way. See this plus 3x on the back? Just make it a minus 3x.
Got it.
Okay? Y'all got that, everyone? I changed that to a minus. So that's minus here. All right. What's the first thing we do?
Make it goes to 0.
Figure out when this is 0. That means I have to take 3x squared plus 4x minus 3 and set it to 0, right?
So you would only move the 3, right?
Well,
Leave the x there.
this right here, the problems that we've had before, like the one we had before this, I believe we had that, right? Or no, was it that? Yeah, it was that, right? That was our derivative earlier from the previous problem. And what I did was I moved the 4 over and then divided by 3. The reason I did that is because I didn't have an x term in the middle. Okay? This has a squared term, an x term, and a constant term. You see that? So this is like your standard quadratic equation. Like this is a quadratic equal to 0. So how do we solve an equation like that? Factor. And if factoring doesn't work? Quadratic formula. So does this factor? Let's see. Does this factor? So remember this thing we did? 3 times negative 3 is negative 9. And then the number in front of x is 4. You have to come up with two numbers that multiply to be negative 9 and add up to be 4. It's not going to happen. Not today. Right? I don't think you're going to be able to come up with two numbers that multiply to be this and add up to be this. It's just not going to happen. All right? So what do you have to use? Quadratic formula. Now, quadratic formula, remember, said that the solutions to a quadratic equation are negative b plus or minus b squared. Remember this? Yes? All of this? Remember that? We have to use that now. Do you understand we can't factor it? Yes. Pardon?
How'd you get the?
How'd I get what?
I just wanted to continue with that. How'd you get negative 3x minus 4? Did you just take out the x?
How to get negative? Oh, no. I was comparing that to a different problem from the problem before.
Never mind.
We were saying, why are we doing this one with the quadratic formula when the one before we didn't? And it was because this one has an x term.
Okay. Thank you.
All right, so this is going to suck. Are y'all ready? This is the reality of life right now, okay? X is equal to, what's negative b? Negative 4. So remember, this is a, this is b, and that's c. And make sure you keep their signs, right? So negative b is negative 4, plus or minus square root. All right, what's b squared for us? That's that positive 4 squared. So 16 minus 4, that's the formula, minus 4 times a. What's a? 3 times c. What's c? Negative 3. And then all of this over 2 times what's a? 3. This is equal to negative 4 plus or minus the square root of. All right, I believe we've talked about this. This part right here, I said just count how many negative signs you see. Do you remember me telling y'all that or not? No? Does anyone? Do you remember me? So count how many negative signs you see. We see 2 of them, right? If you see an even number, then you're going to put plus. If you see an odd number, you're going to put minus. So I see 2 negative signs, so I'm going to put 16, that's this, plus, and now just multiply these numbers together. Don't worry about the signs. 4 times 3 times 3. What is that? 36. So we're going to be adding 36. Then all of this over 6, right? Now, negative 4 plus or minus the square root of, what's this? 52 all over 6. How many answers does this represent? This is 2 answers, right? It's negative 4 plus that number over 6, negative 4 minus that number over 6. And so now at this point, I could get onto my calculator and I could figure that out. Negative 4 plus root 52 over 6, and I could do negative 4 minus root 52 over 6. And I'm going to get 2 solutions, right? There are going to be 2 decimals there. And I'm not too concerned about what they are. Just, I mean, not right here. I mean, whatever you get, you get. Those would be 2 critical numbers. Okay, so we would get 2 critical numbers from this. So I'm going to let you take that the rest of the way. You get the decimals on those. Okay? So we have 2 critical numbers so far. So far. What do we still have to look at? We set the derivative equal to 0. We figured out we needed a quadratic formula. We had to do all that crap, and then we got two numbers, right? But now we need to look at the second thing, which is anywhere where the derivative is undefined. And so look at the derivative. Is that ever undefined? Do you ever see division by 0? Do you have a fraction? You don't have a fraction. Do you see a square root in here? No, right? So you don't have to worry about it. No issues. All right. We're ready to move on to the next idea here, I think. Do y'all feel like you kind of have a basic idea of what we're doing to find critical numbers? Take derivative, set it to 0. Take derivative, figure out where it's undefined. I just want to know, just by a show of hands, if you remember this from 1324. Just tell me if you remember this from 1324. If you have a quadratic function, we know that this is a parabola, right? Right? Okay. That parabola either opens up or it could open down, right? We don't know exactly. We'd have to know what this number is. Do you remember the name of this point on a parabola? What we called that point, either the lowest point on the parabola or the highest point? The vertex. Do you remember that? That vertex, in 1324, we gave it a very special x and y coordinate. We called it h and k. Does that look familiar? No? Okay. So some of you remember it, some of you don't. Do you remember a formula called the vertex formula that said that the h is always negative b over 2a? That's what I really wanted to know. Does anyone remember that when you look at parabolas, that if you want to find the lowest point or highest point, the h here, which is the x coordinate, will always be negative b over 2a? Show of hands. Anyone remember that formula? Okay. All right, that's enough of you. Okay, so what would the slope of the tangent line be here at this point? What would the slope be? 0, right? What would the slope of that tangent line be here? 0, right? So what if I asked you right now to take the derivative of this? Take its derivative. Remember, a, b, and c are constants. So what would the derivative of a parabola be? It would be the 2 would come down, so 2ax plus b, right? And the derivative of this would be 0, right? So if I were to say find the critical numbers for this, you would now take that and set it equal to 0, wouldn't you? So take this and set it equal to 0. First thing you would do is move the b over, right? B would come over, you'd have 2ax equals negative b. Now if I'm solving for x, what would you divide by? 2a. So you get x is equal to negative b over 2a. And this is no coincidence. That's exactly where it comes from. If you have a parabola, you're guaranteed to have a point that's either the lowest or the highest. And that will always be where the derivative is 0. So if you take the derivative and set it equal to 0, you will get that the x coordinate must be negative b over 2a always. So that's the formula we give you in 1324. We say, here's the formula, but we don't actually tell you where it comes from. But here's where it comes from. That's just a side ancillary little piece of information. Well, this will work for any quadratic. So if someone gives you a quadratic, puts numbers here, you can figure out where that vertex is. All right, so how are we going to use this? Critical numbers. How is this going to be useful? Let's see. The whole goal, okay, the whole goal of the next 2 classes is for me to be able to give you a function and for you to be able to tell me where its local maximums and local minimums are. Got that? I give you a function. You have to find where does it reach its highest points and lowest points. Now, tying this back into cost functions, profit functions, revenue functions, this is important in a business perspective. We want to know the highest our profit is, the lowest our profit is, right? So here's how we're going to do it. Let me again try and motivate this with a graph. What if I tell you that I have a graph here of a function, and at this particular point in x, that's the point on the function. That's not a whole lot of information, is it? That's not a whole lot of information. That's just a point on a graph. You can't tell me if that's the highest or lowest point, can you? No, right? There's not enough information being given to you here. So now, let me give you some other information. I'm going to tell you that the derivative there is 0. I'm telling you that. Is that enough information for you to tell me whether or not that's a maximum or a minimum? I think I'm going to start calling on y'all because I'm seeing people are on their phones, people are just kind of drifting in and out. I mean, I'm here to try and help you learn this. You have to be engaged. You have to want to answer my questions, not the same few people, right? So if I have to call on you, I'm going to call on you. Do y'all want to do that? We can. Will it help you if I just start calling on you? Yeah, I don't mind doing it. I think, okay, I'll do it. Why? You don't want to be embarrassed?
No, I could.
Yeah, I mean, who cares, right? I mean, everyone's going to walk out of here. No one's going to be like, that's that girl didn't know the answer in class, man. Shoot. Who cares? We're here to learn, right? Okay, so let me ask you again. If I tell you that this point's on a graph, you can't tell me if that's a highest or lowest point, right? No. If I tell you the derivative is 0, you still can't tell me, right? No. Now, what about this? What if I tell you that to the left of this point, to the left, what if I tell you over here that the derivative is positive? Greater than 0, is that okay with you that that means positive? And over here on the right side, I tell you that the derivative is negative. Then it has to be a what? That point would have to be a what? A maximum. Because over here, the derivative being positive means what is our graph doing over here? It's increasing, right? Because your slope of your tangent line has to look like this. So your graph is going up here, right? And then on this side, your graph has to be going down. That means your graph must do that. Oops, I missed it completely. There we go, right? That must be a local maximum then, right? Do y'all see how just knowing that the derivative is 0 is not enough? But if I know to the left of it, it's positive, and the derivative is positive, and to the right of it, it's negative, then I can tell you that that's a local maximum. So this would be a local max. I'm about to give you a definition, and this is basically what the definition is going to be doing, but not in pictures and words. What if I tell you here, I have a point, and that the derivative is 0? You still can't tell me anything, right? But what if I tell you to the left of this, the derivative is less than 0, negative, and to the right of it, the derivative is greater than 0? Then what must be happening here?
Undefined.
Mm.
It's in the middle.
If to the left of this, my derivative is negative, means my graph is going which direction? Down. Negative derivative means like this, right? The slope of the tangent line, negative, means pitch down, right? So if to the left of this my graph is coming down, and to the right of this my graph is going up, then that means it must do something like that, right? So that would correspond to a local minimum. Okay, now let me put this in words, because the book has it in words. if C is a critical number, and f prime of x is less than 0 to left of C, and f prime of x is greater than 0 to right of C, then what can you tell me? So that's basically this picture right here. We're calling this point C. The derivative is negative to the left, right? And the derivative is positive to the right. The derivative is negative to the left of C, and derivative is positive to the right of C. Then what can you tell me about what's happening at C? Then f of C is a minimum. Local minimum. Local minimum. And then we have another note that says what? The opposite of this, right? If C is a critical number, and f prime of x is greater than 0 to left of C, and the derivative is less than 0 to right of C, then f of C is a what? Local max. So basically, the derivative is telling you everything you want to know about the graph, right? A positive derivative means we're going up. A negative derivative means we're going down, right? So if we ever go up and then down, we're going to have a local max. If we ever go down and then turn back up, we're going to have a local minimum, right? That's what the first derivative tells us. So let's do an example where we put all this together. I'm going to give you that f of x is equal to x cubed minus 12x plus 2. Find where f is increasing, decreasing, find local maximum, find local minimums. So I'm going to find the local max slash s, because you could have multiple local maximums. Remember, you could have multiple hills. And then find the local minimum or minimums. You could have multiple places where you have low points. Now, what does increasing and decreasing mean? What do you think it means? Because I haven't defined it. What do you think that's asking for? Find where the function is increasing. What do you think that would mean we need to figure out? Where's the derivative what? What does that mean, though? The derivative has to be what if we're going up? Positive, right? So this right here means we have to figure out where is the derivative positive. And then this would mean where